Hello, I hope that it finds you helpful. This is the presentation of this article with the title Effect of Cache Runtime Parameters on the Reliability of Embedded Systems. Authors of this paper are Mohammadhasan Ahmadi Livany, Mostafa Salehi, and Kargar. I am Mohammadhasan Ahmadi Livany. I am MSc student in Architecture of Computer Systems at University of Tehran, and I'm gonna present this paper. I hope you find it useful. In this video, at first, I will give an introduction of this paper, then I will have a brief survey on the related works which have been studied before. I will explain simulation setup and I will elaborate the experimental results of this paper and a bit discussion about them, and at last I will present a brief conclusion of this paper. Reliability is the probability of correct working of a system in a period of time. Soft errors that are caused by radiations affect system reliability, and they increases by shrinking the size of transistors according to the trend of technology. It means that effect of soft errors on digital system reliability is getting more critical by transistor scaling. Cache is the most susceptible part of the system against soft errors because of the high transistor density and large chip area. Hence, it is tightly coupled with system reliability. Cache protection against soft errors is based on ECCs, that is the abbreviation of error correcting codes. Utilizing ECCs in cache is not efficient and they expose area, power, and performance overheads to the system. So there are some works on minimizing the overheads of ECCs, and also some works concentrate on using ECCs efficiently at architecture level. For evaluating the reliability of a cache, we need a metric. There is a metric for reliability of a system which is named Cache Vulnerability Factor, or CVF. It expresses the probability of cache errors propagation to other system components. It is a metric that evaluates the susceptibility of data in cache against soft errors. As it is said, CVF is a reliability metric for cache. So, working on improving CVF will improve cache reliability. There are some program or architecture dependent parameters that may affect cache vulnerability. CVF may be influenced by the program which is run by CPU, cache configuration, cache protection, or access patterns of a program to the cache, and also cache replacement policy. Therefore, finding a way for improving cache vulnerability against soft errors is challenging because it is affected by several parameters of the system. Anyway, discovering how these parameters are affecting cache vulnerability will lead to improved cache reliability and protecting caches against soft errors. In this work, we will study the impact of cache configuration on cache vulnerability and will represent runtime parameters which influence cache vulnerability. This figure demonstrates the vulnerable and invulnerable intervals of a word in a cache. Vulnerable intervals are colored by red and invulnerable are green. As it is observed, there are some vulnerable periods, including income read, write read, read, and dirty await. Other intervals are considered as invulnerable. In fact, vulnerability of a word is determined by an access to it. Whenever a read access occurs, means that the word is vulnerable from the last access until now. It means that if a soft error occurs in this interval, the corrupted data will be read and soft error will be propagated to other components of the system. but by a write access, new data will be overwritten on the word, and if there were any corrupted data by soft error, it won't be propagated. In addition, dirty awake intervals are vulnerable because if a dirty data is corrupted by a soft error, on eviction, corrupted data will be overwritten to the lower level of memory hierarchy, and soft errors will be propagated in this case. So, mentioned intervals are critical from soft error occurrence point of view. That's why they are considered as vulnerable. There are some researchers that worked on cache vulnerability. Cache vulnerability is summation of all vulnerable periods of all bytes of the cache. CVF that expresses the probability of error propagation to other components of the system is equal to cache vulnerability divided by total execution time multiplied by cache size. As was mentioned before, replacement policy of the cache affects cache vulnerability. Write-through policy decreases CVF because it minimizes the dirty data inhabitant in the cache. But we know this policy has performance overhead, and replacement policy of caches in embedded systems are based on write-back replacement, which makes cache data more vulnerable. So in this work, we use a write-back cache that is more real in embedded applications. Hong studied the impact of the cache configuration on cache vulnerability for one program, and it is said that vulnerability behaves contrariwise to miss rate because lower miss rate means more data exists in the cache for longer time, so vulnerability will be increased. Although this result was just for one application, and it should be more investigated and more observations we need to analyze the relation of vulnerability and miss rate or other parameters of the cache and program. Partitioning data and instruction caches may cause efficient reliability enhancement. For example, instruction cache includes just clean data, and parity protection will be enough, because if an error is detected by parity, the wrecked data will be replaced by data of lower level of memory hierarchy. That's why we use separated instruction and data caches in our work. It is also mentioned that protection of different cache levels doesn't influence CVF of other levels. It means that if the level 2 cache is protected by single error correction, double error detection that will reduce the L2 cache CVF, it will not affect CVF of level 1 cache, and the L1 cache should be protected separately. It should be mentioned that cache vulnerability is different at different execution phases of a program, and in different blocks of the cache. Hence, protection of cache data can be different at runtime regarding to access patterns of the program to the cache, and ECCs can be used in more efficient ways. Cole has studied about granularity estimation of vulnerability, and it is mentioned that word-level granularity estimation of the vulnerability is more accurate than block-level estimation. Block-level granularity means vulnerability is considered for all words of a block by each access to any word of a block, but in word-level granularity, vulnerability is considered by each access to any word of the cache. Hong represented a protection scheme based on runtime parameters of the cache like miss rate or write-back rate that utilize them for increasing or decreasing cache protection levels. So runtime parameters may help us for efficient protection of the cache. In this work, we have used Gen5 simulator in system emulator mode with classic memory model. We have run programs of automotive MyBench including basic math, bit count, qsort, and Suzanne. Our target cache configurations was combinations of 1 to 32 kilobyte caches and with associativity of 1-way to 8-way. The caches of the system was separated with instruction and data cache, and vulnerability of data and instruction caches are estimated separately. Each instruction or data cache, one of them, is configured on X kilobytes Y-set associative in one configuration, and the other cache is set to a constant 16 kilobytes with random replacement policy. For vulnerability estimation, we have developed a Python code with word-level and accurate granularity. We also extracted the details of vulnerability intervals, including read, dirty evict, and so on. And also, for runtime parameters, we extracted statistics of Gem5 output for each program and configuration. Now we're gonna represent the results of this paper. Here are the average execution time for different configurations of the cache, for Dcache and iCache separately. The left figure represents the average execution time of the program. For different configurations of iCache, that the Dcache is set to 16 kilobytes constant for all configurations, and the right one is the same for Dcache. As it is observed, average execution time decreases when cache size or number of ways are increased. These figures demonstrate the average cache vulnerability for programs over different configurations of Dcache and iCache. The left figure is for iCache and the right one is for Dcache. To be clarified, we have calculated the vulnerability of all programs for each configuration of the cache, and here the average of vulnerabilities of all programs is reported for each configuration of instruction or Dcache. As a reminder, in each configuration of Dcache, the iCache is considered as a constant 16 kilobyte cache, and vice versa is for iCache. For both caches, it is observed that increasing cache size causes growing in vulnerability. It's because of growing the number of words and blocks in the cache. The other point that is observed is about the difference between Dcache vulnerability and iCache vulnerability. Vulnerability of Dcache is much more than that of iCache, and it's because of dirty data in the Dcache. As we know, dirty data are vulnerable from the last access to them until they are evicted from the cache, which just occur in Dcache. iCache data are clean, and naturally it is less vulnerable than Dcache. As it is mentioned, estimating the cache vulnerability is a challenging work because cache vulnerability depends on several hardware and software parameters. To find a relation for cache vulnerability estimation, we investigated Gem5 outputs for programs and benchmarks and also details of vulnerability for each of them. These figures are comparing variation trends of average vulnerability and read share for each of them. As it is observed in these figures, it is found that read intervals are the most effective part of vulnerability in iCache, and for Dcache, read intervals are following the trend of vulnerability for different configurations, approximately. Based on these figures, it can be said that on average of programs and totally, read accesses are the most important cache vulnerable, making accesses in the cache, and read operations can be considered for estimating the vulnerability of both iCache and Dcache. If the read intervals of vulnerability that is demonstrated in previous slide is divided by execution time, the average existing words in the cache during a program run will be obtained. We will name this as running words. Running words are average number of words that are inhabitant in the cache and are read during a program. Hence, if these words are read, vulnerability will be increased. In fact, they are making the vulnerability of cache. That will happen on any read-hit operation in the cache. Hence, hit rate multiplied by running words will estimate vulnerability as it is observed in the figures. In these figures, the blue line demonstrates the vulnerability for each configuration of the cache, and the red line demonstrates the estimated vulnerability. The red line is obtained by multiplication of hit rate and running words, and it can estimate the vulnerability of each config for both iCache and Dcache. This formula works for iCache more accurate than Dcache, although for Dcache it can estimate the trend of Dcache approximately true. So if we know how many words exist in the cache and how much they are hit, the vulnerability can be estimated. Now we represent a formula for cache vulnerability estimation by some runtime parameters, but what about CVF? Regarding to its formula, if we estimate the vulnerability, and by knowing the size of the cache in a determined and predefined period of time, CVF can be estimated. In fact, we will have an estimation of reliability of cache. The results are discussed here. As it was mentioned, cache vulnerability increases when cache size is increased because of growing the number of cache words. The cache vulnerability is about 3 times greater than that of iCache on average. This huge difference is because of dirty data. It means that protecting dirty data is critical, and dirty data have great impact on vulnerability of a cache. As it is observed, vulnerability is influenced by changing the number of cache ways in a constant cache size. It is because of varying data residence among cache configurations. In a constant size, by changing the number of ways, the vulnerability trend may be different for different programs, and it may be increased or decreased. It means changing the number of ways, for example, increasing the number of ways, doesn't necessarily increase or decrease the vulnerability of a cache, and an offline profiling of a program can clarify it. It demonstrates that cache configuration affects the cache reliability. Therefore, designer can choose a more reliable configuration for an embedded application. Indeed, it can remove protection overheads from the system without suffering from complicated designs or implementations. In this work, we introduced some runtime parameters that can estimate the cache vulnerability. These parameters including hit rate and running words. Multiplication of the number of running words and the cache hit rate can estimate the vulnerability level of a cache. This formula expresses that how many words exist in the cache and how much they are read by CPU, and how they are vulnerable. The way of utilizing of these parameters for a runtime application can be explained by this example. Assume that the Dcache is protected by single error correction and double error detection scheme. By monitoring hit rate and running words in a predefined period, we can estimate the level of vulnerability. During a predefined period, if it is diminished, it means that vulnerability is diminished. So it can be alerted to the system that it is working in a safe place, and system protection from Dcache can get weaker. Therefore, the CPU and the system can work in a more efficient manner and the protection overheads will be decreased. In another scenario, consider that the system is working with cache of configuration A. The formula that was represented alerts the system that the vulnerability of the system is increased. So the system reconfigures the cache and changes it to configuration B, that it knows that this new configuration is more reliable than the previous one. Therefore, the probability of soft error propagation through the system is reduced, and also the reliability is increased. So our introduced parameters can lead to an adaptive and efficient protection from caches of the system. In this work, we studied the cache vulnerability and reliability for different configurations of the cache. It is shown that increasing cache size increases cache vulnerability, and cache configuration may affect the cache reliability. We have introduced some runtime parameters that are represented for cache vulnerability estimation. These parameters are hit rate and running words that can be used for runtime vulnerability variation estimation. Vulnerability estimation can lead to CVF calculation, and in this way, cache reliability will be obtained. As it is said, the parameters can be used for runtime applications and monitoring of the state of vulnerability of the cache, and protection can be changed by considering the vulnerability variation with represented parameters at runtime for system efficiency, and they can lead to an adaptive fault-tolerant cache at architectural level. Thank you for your attention.